In this short video, what we'll do is we'll try and build a case for key rate duration. Now, duration is something which we've studied in the one-factor risk metrics and hedges chapter as an interest rate risk measure that helps us arrive at, let's say, a percentage change in the price or value of a fixed income security when the underlying interest rate risk factor changes by a certain amount. So by design, this duration, which we've studied in that chapter, is a single interest rate risk factor measure, and it concerns itself purely with parallel changes in the interest rate term structure. So let's write down the definition of that duration first before we begin. So duration, we have defined it as it's equal to minus 1 over P dP over dy. Okay, so it's basically the sensitivity of or the rate of change of the price of a fixed income security with respect to that chosen interest rate risk factor. Most popularly, this interest rate risk factor y is the yield to maturity, and then I'm further scaling this sensitivity by 1 over p. P is the current price of my security. If I were to tweak this formula around, the way I use duration is it helps me arrive at, let's say, the change in the price of my fixed income security, which is given to be as minus d times p times the change in y. Okay, now let's do this. Let's take an example of a bond. Let's say it's a bond which pays a 6% coupon. The 6% is annual, but it's paid on a semi-annual basis. The maturity of this bond is 5 years, and the face value that I'll be working with is 100. What I'm assuming here is that the valuation of this bond is carried out using a spot rate term structure. It means that spot rates vary with the term, okay, or time to maturity. So what is given to me is a very simple spot rate term structure, which starts with a rate of 3% for a 6-month term and increases linearly to 7.5% for a 5-year term. So let's do this. Let's work out the value of this bond, and then let's slowly and steadily build a case as to where and why we need to graduate away from this concept of duration to the key rate duration. So let's do this. Let's write down all the cash flows which this bond has to offer. Because it's a 6% bond paid semi-annually, the cash flow on every coupon date, which is every 6 months, will be $3, and at the end I receive the principal plus the last coupon, so 103. Use these spot rates. I'm assuming these spot rates are all quoted with a continuous compounding. Compute the discount factor. Using these spot rates, it's simply e to the power minus the spot rate, let's say for any term I, that times ti. So that's my discount factor. Then let's just do this. Let's just take a sum product of this column, which is cash flows, with the discount factors, and you will arrive at the current value of this bond. So before I move ahead, actually, let's also invoke another definition of duration that I know, and that's the weighted average of the times at which my instrument pays me something. And here that something is all the coupons. And then finally the principal plus coupon. So what exactly is this weight? If you remember, the weight which I use to compute this weighted average time is basically the present value of the cash flow, which is paid at the time ti, that divided by the total price of this security. So all that I have to do to compute this weight is take the cash flow, which is, let's say, 3, that times the discount factor, which is this, that divided by the price, which is this, and I get the weight which is given in column F. So first check, if you sum all the weights, you get a 1. Then just do this, just do a weighted average. That means a sum product of column B with column F, and you get your duration to be 4.3452968. Okay, so this is my duration, although it's computed using a different definition altogether. Okay, now this is where I stand. Now let's do this. First and foremost, what I have done here, the way I have presented this problem, is that I'm not really working with a yield to maturity or Y. What I'm working with is a set of spot rates. So therefore, if I were to write down the way I value my bond, it's not really valued like this. It's not valued as price arrived at using a single interest rate Y. Remember the definition of YTM? It's basically that single discount rate which I use to discount all the cash flows of my bond to arrive at the price of the bond as it trades today. So that's the Y. Think of the Y to be like a summary number or a single discount rate number which captures information both with regards to the spot rates as well as with respect to the cash flow profile of my bond. It distills both these set of information into a single number Y. So what I have done here is, in arriving at this price, I have not really used this kind of a valuation, but rather what I have used is price is arrived at basically using a function. Let's denote or think of this P to be like a function F. So let's write it down as a function actually. So I have written the price as a function of 10 spot rates, these given in column D, R1, R2, R3, all the way till R10. Let's write it down. So it will be price, which is a function of R1, R2, all the way till R10. That's the first change that I have done. It's a single variable valuation had I used the YTM to a multivariable valuation where I am using 10 different spot rates to do my valuation. Now let's do this. Based on this formula or this function, let's try and write down a first order approximation of the change in price of my bond if any of these rates were to change. Let's try and do that. So it will be the partial sensitivity of this pricing function F with respect to, let's say, the first spot rate R1, that times the change in R1, let's say the actual change in R1. So it's like sensitivity times the actual change. And let's repeat this for all the 10 spot rates. So then I'll get the partial sensitivity of this pricing function with respect to the second spot rate, that times the actual change in spot rate, all the way till partial sensitivity of this pricing function to the 10th spot rate, that times the actual change in the 10th spot rate. Okay. Now, why is it a partial sensitivity? Because when I compute this sensitivity, I only change this variable. That's it. I don't change any other variable. They stay in their original values. Okay, so that's about the partial sensitivity. Why is this an approximate formula? Because an accurate formula would include higher order derivatives as well, the second order derivative, third order, and so on. And I'm not including those there. So I should actually write it as approximately. Okay. Now let's do this. Let's look at this formula and actually let's interpret it using this relation. So it's dP over P is minus D over dy. This LHS is basically the percentage change in the price of my fixed income security. So let's get this formula of ours into this form. So for that, what I'll do is I'll divide throughout by P. So it'll be this, every term gets divided by 1 by P. Okay. Now I'm trying to actually get everything in the format which I already know, because that will help me define the key rate duration in a way which is very similar to the way we define the normal or regular duration. Okay. Now there is a minus sign missing here. Okay. So let's do this because there's a minus sign here, right? So let's do this. Let's rewrite this formula as dP over P is equal to minus, and then let's put a minus inside. So minus 1 over P dow F over dow R1, this times delta R1, minus 1 over P dow F over dow R2, this times delta R2, all the way till the 10th spot rate. So let's do this. Let's denote this term in the bracket to be a new measure. Let's call it the key rate duration. Let's denote it as, let's say, D1. Think of this key rate duration to be computed using the sensitivity of the price of my fixed income security, which in this case is a very simple bond, with respect to only changes in that particular rate. And that's why key rate duration is linked to one choice of a rate. All other rates are kept constant, or I should say all other rates are kept unbumped. Okay, so that's how I define my key rate duration. So I'll get the percentage change in the price of my security is minus D1, that times R1, minus D2, that times R2, all the way till minus D10, that times R10. Now, before I get to these calculations and show what I have done, let's do this. Let's try and convince ourselves if this formulation subsumes or incorporates within itself our original regular duration concept or not. Okay, so to do that, remember the opening statement I made about duration. I said it's an interest rate risk measure which concerns itself with parallel moves in the interest rate term structure. It's to do with parallel movements. What does parallel movement mean? It means that the rates corresponding to various terms, they all shift by the same amount. That constitutes a parallel shift. So in this formulation, let's do this. Instead of allowing for different shifts for the different spot rates, and here, by the way, I think qualify this previously. When I say key rate duration, then key rate duration is the first step in doing or calculating a key rate duration is to specify what your choice of key rate is. And in this video, the case which I am presenting is one in which key rate refers to a spot rate. Later on, when you actually go into depth in this chapter on multi-factor risk metrics and hedges, the popular choice of key rate is actually the par rate. Okay, but just to clarify concepts, here I'm saying key rate, let it be the spot rate, and when I define the key rate duration, it's with respect to changes or shifts in a spot rate that has been chosen as the key rate. Okay, now let's do this. As I said before, let's use same shifts for all these individual key rates. That means let's replace all these with the same delta R. Okay, so when I do this, what do I get? I get something like this. It's minus D1 plus D2 all the way till D10, that times delta R. It's telling me that if I were to sum all the key rate durations arrived at, let's say, using these formulas, then what I get actually should be, let's say, very close to this regular duration. Okay, so let's do this. Let's now put all these concepts to action for this choice of bond that we've done. To begin with, let's start with computing these sensitivities, and by sensitivities I'm referring to this formula. It's the change in the price of my bond, which is, let's say, given by this function f, when one of the spot rates changes and the other spot rates are held the same. Okay, now this choice of this computation of sensitivity can be done using two methods. Either you can do it using an analytical method, which is very much possible in this case, because if you were to write down the pricing formula, something like this, the formula which would calculate this number, you would find that each of these spot rates only appears in a single term. It's only appearing as a discount factor for the relevant cash flow which this spot rate is used to discount. So all you can do is quickly compute the derivative of that particular term with respect to Ri, because all other terms in this valuation formula are not affected by this Ri, okay, the ith spot rate. So that's the analytical way of doing it, just by doing a differentiation. Okay, the numerical way of doing it, which is the second possibility, is also very simple. All you have to do is just take the spot rate. Let's say I am computing the sensitivity of the 1.5 year spot rate, which stands as 4%, all that I need to do is just bump it up by 1 bp, note the change or note the price which the bond has after this bump it down by 1 bp, that means to 3.99%, note the price, take the difference of these two prices, that means the price in the upstate, price in the downstate, and divide it by 2 bips, because that's the change in the spot rate between the up and the down. That's a numerical way of computing this sensitivity. Either way you do it, the results won't be that off for this very simple product. So what I have done is I have actually computed this sensitivity using bumping, and then what I have done is I have basically added all these sensitivities. Okay, so if you add all these sensitivities and divide it by the price and put a minus in front, you've basically computed this term in the bracket. And what I get for this is this. Look at how close this number is to the duration that we have got as the weighted average of all the times at which cash flows occur. Look at how close these two numbers are. Okay, so that basically proves our conjecture which we had, that the sum of key rate durations should be very close to the duration, the regular duration. Okay, so this was about, and actually why is it not exactly equal? It should have been exactly equal in this case, but it's not exactly equal because the sensitivities here are computed using the numerical route, not the analytical route. That's why they are very close but not exactly equal. Okay, that's about calculations till this point. Now, what is the key rate duration? Simply take this sensitivity, that's this part, divide by price and negate it. You will get the key rate duration. Okay, now let's do this. Now let's play around with various choices of these delta R1, delta R2, and so on. That means if I have at my disposal the key rate durations of this bond, I am well equipped now to actually work out the percentage change in the price of my security for non-parallel shifts of the interest rate term structure. That's where key rate durations come in. They help you work out the impact of interest rate changes for shifts that are non-parallel. Remember, duration only concerned itself with parallel shifts. So to understand and see how key rate durations would come in and help, let's start off with the simple shift in term structure, and that's a parallel shift. If I were to shift the entire term structure parallelly, let's say by 1%, all rates get shifted by 1%, which is shown here. The blue term structure is the original base one, and this orange one is the shifted one. So I can do two things. After performing this shift, I can compute the value of my fixed income security by a revaluation. So that is the number which I obtain here. All that I am doing here is take the shifted spot rates, convert them into discount factors, do a sum product of column K with column C, which is my cash flows, and arrive at the new value of my bond. That's like a revaluation. Now this revaluation will give me the exact impact which this change or shift in the spot rate term structures would have on this particular bond's valuation. And then what I do is I try and get an approximate impact of the shift in spot rates by working my way through duration. So if it's a parallel shift in the spot rate term structures, I can use my regular duration. If it's a non-parallel shift, I'll use individual key rate durations multiplied with individual spot rate shifts. Okay, so take a look at how the exact and the approximate compare to one another. See, the exact is minus 4.24 and the approximate is minus 4.34. This highlights another concept that we've done, and that is when you take a look at a duration based impact, then duration is a first order derivative. When we are using this duration, we are actually doing a linear approximation, and that linear approximation in this particular case tends to overestimate the loss. And see, it's indeed doing that. It's overestimating the loss by around 0.1%. Why is that so? See, the price versus yield I know is convex. If I stand here as my current, let's say current yield or the current rates, And if I were to shift the rates up, then the duration based impact would get you somewhere here, while the true impact is somewhere here. That means duration based is overestimating the impact. Now, all good till now. Now let's do this. Let's now put the key rate durations to use. To do that, let's switch from parallel shifts this time to non-parallel shifts. Let's begin with a very simple non-parallel shift, and that's a steepening. So in a steepening, see what has happened. Long-term rates have shifted a lot more than short-term rates. To get the impact of this shift in the spot rate term structure, just pick the key rate durations, multiply each one of them with the individual spot rate shifts, something like this formula, okay? And the approximate impact that you get is given by this, okay? And see how close it is to the actual impact. Why is the actual and the approximate so close every time? Actually, they are close because my shifts are not that big. If I were to use huge shifts, let's say 4 or 5%, for example, then these will be not as close as what you see right now. Okay, so the closeness means that linear approximations seem to be working fine because your shifts are not that big. Let's check other kinds of shifts as well. So let's move to a flattening. So flattening happens when short-term rates, they move up by a lot more than long-term rates. And yet again, you see that the two are quite close. I mean the exact impact and the approximate impact. Let's check for change in curvature. So initially my spot rates, let's say, were linear, and now let's say I have bumped them to make it a curved term structure of interest rates. And again, the exact and the approximate are not that far, it's quite close. So what has key rate duration helped us with? Key rate durations, they have helped us with arriving at the approximate impact which non-parallel shifts in the spot rate term structures will have. This kind of a change or shift in interest rates would be a scenario in which duration might not be, the regular duration might not be an appropriate measure to use to arrive at a quick and approximate impact. Okay, so this was like a quick kind of overview of this shift or graduation from, simple regular duration, which is the one factor risk measure, to this concept of key rate duration. Now, individual key rate durations do concern themselves with a single rate. But then what we are doing is basically we are computing a duration for each of these rates so that each of these durations can help us, when properly scaled by the actual shifts in these rates, each of these key rate durations put together, they can help us arrive at the percentage change of my fixed income security for non-parallel shifts in the spot rate term structure. So this was the intent behind the video, just to explore as to when I would need key rate durations, how to compute them, and how to put them to use to compute the impact of shifts in interest rate term structures.